So we have been discussing ordinary differential equations. Specifically, we've been looking at Laplace transforms and how, with the aid of Laplace transforms, we can, this will play out nicely with differential equations. Right. So it's in this direction we're proceeding, and so there is a key operation involving functions which we want to discuss in this lecture, which will help us calculate Laplace transforms in an effective way, and that is the idea of convolution of functions, right, which is the subject matter for this lecture. Okay, so the reason why we are interested in the convolution operation, which looks like a convoluted operation, which we will define in a moment, is that what looks complicated in one domain turns out to be fairly simple in the other domain. Namely, when you take the Laplace transform of a convolution of two functions, it is going to turn out to be very simple, as we will see. So, but let's start with the definition of this convolution. So, if you take two functions f of t and g of t, well, I mean, for the purpose of Laplace transforms, we are looking at functions which are defined for positive t, right? But we will see later on how this can, the idea of convolution can be extended to functions which are defined from minus infinity to plus infinity, whose the variable t, when it takes all values from minus infinity to plus infinity. So the operation is the following. So you take these two functions f of t and g of t, and then you integrate. So you take the product of f of t times a shifted version of f of tau times a shifted version of this function g of t minus tau. It's like a correlation function in some sense, but you have to shift one of these two functions by an amount which is t minus tau, right? So you take the value of the first function at tau, and the other one is taken at g of t minus tau. You take the product of these two, and then you integrate over all tau. Tau goes all the way from 0 to t, right? And so if you do this operation, so let's see what happens if you change this variable. So it looks like it's apparently treating the function f differently from g, right? So but if you change this variable t minus tau to x, we have f of t star g of t is the limits of integration now will go from t to 0, because it's x that we're integrating. So if tau is 0, then x is t, and if tau is t, you get x is 0, and then you get a minus sign because d tau is minus dx. And now in place of f of tau, we have f of t minus x, and in place of t minus tau, of course, we have x. So we have f of t minus x times g of x, but you have a negative sign here which you can absorb into this integral. If you change these limits, instead of it going from t to 0, if you make it 0 to t, this negative sign goes, and so we see f of t star g of t is the same as integral 0 to t g of tau f of t minus tau d tau. So you see that this is as if you have reversed the role of f and t compared to this definition. Therefore, indeed, f of t star g of t is the same as g of t star f of t. It's completely symmetric, so there is no issue with this definition, right? So this is an operation which takes two functions f of t and g of t and gives you another function, right? And so why would we bother doing something so complicated? So the reason is that if you take the Laplace transform of such a function, so let's see what happens if you take the Laplace transform of a convolution, right? So I have f of t and I have g of t. So if I take the Laplace transform of the convolution, so the convolution itself is defined like we just saw as this integral 0 to t f of tau g of t minus tau d tau, and then I have to put in this factor e to the minus s t, and then I integrate from 0 to infinity. There is a dt which comes in at the end. So if I do this integral, so I get a double integral now. So I have 0 to infinity and integral 0 to t e to the minus st f of tau g of t minus tau d tau dt, right? So this is a double integral. So let's look at this pictorially. So it's helpful to see what is going on here. So I have my tau and t. I plot my tau along the x-axis and I plot my t along the y-axis. So if I fix the value of so first of all, so the way I'm doing this double integral is I will take t to go all the way from 0 to infinity, but that happens in the second step. So if I fix my value of t to be some value, so right like here, and then I will take tau to go all the way from 0 to t, and then I will allow t itself to go all the way from 0 to infinity, right? So that's what is going on here. So I have some function here which is some function of t and tau, right? And then it's just the limits of this integration are from, first of all, I fix t and take tau to go from 0 to t, and then I allow t itself to go from 0 to infinity, right? So basically I'm covering this entire region which which lies above this line t equal to tau and to the right of the y-axis. This entire region is covered. But I mean, the same region I could think of in a different way. I could construct using strips which are along vertical strips instead of horizontal strips. If I looked at horizontal strips, I got this region of integration I could cover using these limits. But if I could also construct the same region, ultimately you are doing a double integral over some region, right? So instead of doing summing over all these horizontal strips, I can also think of summing over these vertical strips. So if I do this, then I see that how would I do this? I would fix tau to be a certain value and allow t to go from tau all the way up to infinity, right? So I could do this instead of, so the same integral, double integral, I could perform if I fix if I allow t to go from tau to infinity, I fix tau, and then tau itself goes from 0 to infinity, right? So you just have to look at this picture and convince yourself that this is reasonable, right? So look at, I go to a particular point, look at one strip. So what have I done? I have fixed tau to be some value. You see, tau itself can take all values from 0 to infinity, but if I fix tau to be a certain value, right, I mean, you're supposed to think of a strip tau to tau plus d tau. Within this strip, I see that t cannot take all values. T will take only values from tau, or after all, you're going to cover this same region as here, right? And in order to do this, I will restrict t to go from tau all the way up to infinity, right? So why do I bother doing all this? So you'll see in a moment. So now it helps me with this change of variables. If I change my variables and I allow u, I make u is equal to t minus tau, which will go from 0 to infinity, and v equal to tau, which also goes from 0 to infinity, right? So you see that t minus tau is this entire region above. After all, t goes from tau to infinity, so t minus tau will go from 0 to infinity, and v is just tau. After all, you see tau is just going from 0 to infinity. So the limits of u and v are easy to fix if you do it this way. And then you have, in place of t, I have to put u plus tau, which is the same as u plus v. So I have e to the minus s times v plus u, and in place of f of tau, I have f of v, and in place of g of t minus tau, I have g of u, right? So you can work out the Jacobian, and that's going to be just unity. So you just get du and dv. In place of dt, d tau will go to du dv. So we have converted one double integral to another double integral involving some different variables. And why did we bother to do this? It's because now we have both u and v being treated the same way, basically. So now, in fact, you can separate out these two and write it as two integrals. It's the product of two integrals, two single integrals. The double integral has been decoupled in some self using this change of variable. So I have 0 to infinity e to the minus su g of u du times 0 to infinity e to the minus sv f of v dv. So which is nothing but the Laplace transform individually of each of these functions, right? So it's, this is the Laplace transform of f and this is the Laplace transform of g, so it doesn't matter in which order I put it. So the key point is that I have shown that the Laplace transform of the convolution of two functions is the same as the product of the Laplace transforms, right? So what is a complicated operation in time domain is just simply a product operation in the the Laplace transform space, and that's where the power of this method comes from, right? So let's look at an example of how this plays out. So suppose we wish to find the inverse Laplace transform of this function f of s is equal to 1 over s times s plus 1. So this is something that we know how to do, right? We could just rewrite this function as 1 over s minus 1 over s plus 1 partial fraction expansion, and then we know how to take the inverse Laplace transform of 1 over s. We know how to take the inverse Laplace transform of 1 over s plus 1. So the answer is simply given by 1 minus e to the minus t, right? So as you can verify by taking the Laplace transform of this function, and you'll get back the same function that we started with. But let's work it out using the convolution property. So what is this? We have the inverse Laplace transform of f of s is the inverse Laplace transform of the product of these two functions. But we have seen that what is a product in this Laplace transform space becomes a convolution in the time space. So that is inverse Laplace transform of 1 over s convolution inverse Laplace transform of 1 over s plus 1, each of which we know how to do. So it is just function 1, and when I say put 1 here, it's the function f of t is equal to 1 convoluted with e to the minus t, and this is nothing but integral 0 to t 1 times e to the minus t minus tau d tau, which is simply e to the minus tau minus t, right? So it's an integral over tau. So tau minus t 0 to t, and immediately we get if I put tau is equal to t, I get 1, and if I put 0, I get minus t. So I have indeed 1 minus e to the minus t, which is exactly the same result we obtained directly earlier, right? So this is a very simple example where we had an alternate, even easier method to evaluate the inverse Laplace transform by. But there are other places where, in fact, this convolution, operation is a useful way of computing the inverse Laplace transform. So definitely this is an important property to be familiar with. So let's look at also the idea of the Fourier transform of a convolution, right? So just like the Laplace transform of a convolution has this very nice convenient form, we can also look at the Fourier transform of a convolution, and we will see that there is something simple which emerges there as well. So we have two functions f1 of x and f2 of x. So now it's the Fourier transform, so you have to do an integral all the way from minus infinity to plus infinity. We have this factor 1 over 2 pi, right, because that's the convention we are following. So we have 1 over 2 pi integral minus infinity to plus infinity f1 of x e to the minus I alpha x dx, and g2 of alpha is 1 over 2 pi integral minus infinity to plus infinity f2 of x e to the minus I alpha x dx, right? So if you take the product of these two functions, the Fourier transforms, then we have g1 of alpha times g2 of alpha is equal to 1 over 2 pi the whole squared integral minus infinity to plus infinity, again integral minus infinity to plus infinity. So we'll use some other dummy variables here. After all, these are getting integrated out. If you put the same x, you'll run into difficulties. So we'll say du dv f1 of u f2 of u times e to the minus I alpha times u plus v. Now we make the change of variable x is equal to u plus v. So we have integral 1 over 2 pi the whole square integral minus infinity to plus infinity integral minus infinity to plus infinity du dx f1 of u, and in place of f2 of v we put f2 of x minus u, and we have e to the minus I alpha x. So then we see that in fact we can write this as 1 over 2 pi the whole square integral minus infinity to plus infinity dx e to the minus I alpha x. We can pull out this factor, and then we have this integral minus infinity to plus infinity du f1 of u times f2 of x minus u. So if we look at this integral which is given in the square brackets, it is something similar to what we have seen. So in fact we can define this as the convolution of two functions which are defined all the way from minus infinity to plus infinity. So it's a full integral minus infinity to plus infinity du f1 of u times f2 of x minus u. So this is also like taking a function, taking the other function, you have to uh, shift it, but also there is a minus sign that you have to take and shift it by an amount to, and then overlap the two and then integrate, right? So that's what this operation is. It's like a correlation but with some shift involved. And if you do this, so then we see that in fact the product of these two Fourier transforms is nothing but, this is like taking the Fourier transform of this convolution, but you have to be careful. There is also a factor of 1 by 2 pi involved. So what we have managed to show is the Fourier transform of 1 by 2 pi times the convolution of these two functions, f1 of x star f2 of x, defined in this manner, is simply the product of the Fourier transforms g1 of alpha times g2 of alpha, right? So this factor 1 over 2 pi appears in this manner because of the convention we have used for our Fourier transform definition and the inverse Fourier transform, so on, right? If you had used a slightly different convention, we would have different factors. But the key point is that what is a convolution in one domain becomes a product in the other domain, just like we saw for Laplace transform. So indeed here it turns out that if you take the product, within this convention, if you take the product of these two functions, f1 of x times f2 of x, and take its Fourier transform, it's going to be just the convolution g1 of alpha convoluted with g2 of alpha. So this is something that we will allow you to verify yourself. But the key idea is, what is a convolution in one space will become a product in the other, and that is a property which often we try to exploit, because products are easy to work with and convolution is a much more complicated operation. Okay, so that's all for this lecture. Thank you.